Hi, today we're going to be taking a look at the integral test. Now this is a test that we can use if the nth term test fails. And it's very simple to use. We're going to talk a lot about this as we go through the process. It says if a function is positive, we'll talk about why that is, continuous and decreasing for any values greater than 1, and we can let a function equal a summation, then it says that the summation and the integral itself from the summation will either both converge or both diverge. Now, what this is kind of telling us is the following. If the nth term test fails, we have to come up with another way to find out if it converges or diverges. And what the integral test is telling me is saying that, well, I can't find the sum because the nth term test will fail, so I'm going to take the integral itself instead. Now, if you recall, a summation only adds up integral values. The sum at 1, the sum at 2, and at 3, and at 4, and so forth. So, but an integral sums up everything, even in between. So, for example, most basic one, like let's say we take the first and second term are 1 and 2. If I add them together, 1 plus 2 is 3. But an integral will take up everything. It's not just adding the 1 and 2, but everything in between. 1.1 plus 1.2, it's going to add up all sorts of little tiny little values. So this number right here is actually going to be bigger than our summation itself. So kind of the rule of thought, what kind of goes in my head? If this converges, and it's going to be bigger than my summation, then my summation must converge also. So, and that's why we say it has to be positive. So we say that, so therefore we can kind of say that the integral of f of x dx has to be greater than the summation on the same domain. And that's why it has to be positive. Now we'll talk about the remainder in just a little bit. So we want to know whether the following series will converge or diverge. So if I try the nth term test, and you always should try it because it's the easiest one, you can even do it in your head. If I try the nth term test, I'm going to take the limit as n goes to infinity. I get n over n squared plus 1, and that equals 0. So it's not saying that it converges. Remember, the nth term test says if not equal to 0, we diverge. It doesn't say if it equals it converges. It just means that the test fails. So we can say that the nth term here fails. Let me get my light back on here. Okay. It says that the nth term test fails. So because it fails, we got to take another test. And that's where we get the integral test. So what the integral test says, okay, well, since my nth term fails, let me try something else. So I take a look. Is this going to be a positive function always, from 0 to infinity? Yes. So we have to say this. People hate this part. F is positive. You have to write that out. Is this function continuous? Yes. We're going to take an integral. That's why it has to be continuous. Yes. There's no holes, gaps, or anything like that. Is this function decreasing? Now you can do this in your head. Okay, is it decreasing? I'm going to get, if I let n be 1, I get 1 over, what's that? 5. If I let n be 2, I get 1 over, sorry, if I'm 1, that's 1 over 2, sorry. This becomes 2 over 5. 1/2, 2/5, it's going to get smaller, 0.5, 0.4. It gets smaller, so it's decreasing. Now the reason why it has to be decreasing, very logically, I want to see if this converges. It can only converge if the numbers get smaller. It has to be decreasing to converge. In other words, if this numbers were decreasing, if this was increasing, well, what would happen? That's right. If it was increasing, the series would diverge, and we wouldn't have to do this test anyways. And the nth term would catch that. If the nth term test would catch if it was increasing, because it would diverge. Now, so what we're going to do, and this is now, we just said decreasing, so what we do is very simple. After you show it's positive, continuous, and decreasing, we have to write this as an integral. So here's what the rule says. I'm going to let a sub n equal my function. So I'm going to let my function equal, instead of enso, x over x squared plus 1. And I take the integral there from 1 to infinity of x over x squared plus 1 dx. Now hopefully you kind of recognize something, an improper integral. So I have to rewrite this as the limit as b approaches infinity of my integral 1 to b x over x squared plus 1 dx. Using u substitution, u is x squared plus 1, du is 2x dx, dx is tu over 2x. Those x's will cancel. Now if you recall, this whole bottom here is just u. So when I integrate this, and I can do this real quickly, I'm going to get this limit as b goes to infinity. I'm going to go ahead and integrate this 1/2, though, don't forget the 1/2. And this is just 1 over u, so I get the natural log of u, which is our x squared plus 1. And this is going to go from 1 to b. Take a moment and verify that if you need to. Taking the using the FTC now, using the FTC, we're going to get the limit as b goes to infinity of the following 1/2. I just write it all in. The natural log of b squared plus 1 minus the natural log of 2. Because if I plug the 1 in, I get 2. Now, as b goes to infinity, what happens? Well, this gets bigger and bigger and bigger. Natural log of 2 doesn't really matter anything. Take infinity minus the natural log of 2. Still infinity. So this grows infinitely large. So what is this telling me? Well, it tells me that my integral diverges. That the integral diverges. So remember what I told you. If the integral diverges, and we know that the value of the integral is going to be bigger than the value of the summation, well, if the integral diverges, then the summation is always going to be one step behind the integral itself. So therefore, we can actually say that the series diverges as well. Diverges by what we call the integral test. And you have to put down the reason. You have to put down the series, sorry. We should say the series, excuse me. We got to put the series diverges by the integral test. We got to put the word series there. And you have to identify it as a series, not as a sequence, okay? All right, so let's try part B here. So same thing. If I try the nth term, always try it. You never know. If I take the limit as n goes to infinity, this becomes 1 over n squared plus 1. We get 0. So again, the nth term fails. Yes, right? So we're going to use the integral. So I have to say, is f positive? Yes, that's always going to be positive. Is f continuous? Yes, it's going to be continuous on that domain. Is f decreasing? And again, I can do that. Plug in 1. 1 over 2. Plug in 2. 1 over 5. So it's getting smaller. So yes, it is decreasing. So if it's positive, continuous, and decreasing, you have to say this. What we're going to do is we're going to let the function equal our sequence here. X squared over 1 plus 1. And I write it as an integral. I do the integral down. From 1 to infinity, 1 over x squared plus 1 dx. Yep, another improper integral. These will always be improper. We take the limit as b goes to infinity. 1 to b, 1 over x squared plus 1 dx. And yep, you should recognize that this is our arc tangent. So we get the limit as b goes to infinity of the arc tangent of x. And that's going to go from 1 to b. So using the FTC, we get the limit as b goes to infinity of arc tangent of b minus the arc tangent of 1. Now we've done this enough. As b goes to infinity, the arc tangent of infinity is pi over 2. The arc tangent of pi over 1, is pi over 4. So if I subtract, I get pi over 4. Now notice, this one ends. This converges. So what is this telling me right here? This tells me that the integral converges. That the integral itself converges. Now, therefore, what's that telling me about the summation, the series itself? Well, remember, if the integral converges, and the integral, again, is always a little bit bigger than the summation, well, if the integral stops, then the summation must stop as well. Therefore, we can say that the series also converges as well. Converges by the integral test. Now, danger, danger, danger. We're not saying that the series converges to pi over 4. The integral converges to pi over 4. Remember, the series is right behind it. We don't know what the series will converge to, and that's the beauty of these tests. They tell me that it will converge, it'll end somewhere, but we don't know where. So very carefully note, the series does not converge to pi over 4. We don't know what it actually converges to, okay? We don't know, and that's the beauty of what we're doing here, okay? So, because it's like pi. Pi converges. We just don't know what it converges to. If you figure that out, you can make $1 million easily. So, go on to part 2, and we'll talk about the error in the integral test. All right? Bye-bye.